welcome back to another Discrete Math tutorial. This time I thought we'd cover tautology versus contradictions. So what is a tautology? A tautology is a compound proposition that is always true, and a contradiction is a compound proposition that is always false. If we look at this example, P or not P, regardless of what the truth value of P is, not P is always going to be the opposite value. So if the truth value of P is true, not P would be false. True or false is equal to true. Now, if the truth value of P is false, not P would be true. So false or true, again, is true. Similar concept goes for here, except with the and symbol. And remember, can only be true if both of the truth values are true themselves. So true and true would be the only time this could equal true. As you can see, whatever the value of this is, let's say this is true, well then this is going to be false, so true and false is going to be false. So that is a contradiction. There is one more concept that is neither a tautology nor a contradiction. A compound proposition that is neither a tautology nor a contradiction is called a contingency. The next concept that we have to introduce is called logical equivalence. And logical equivalences are compound propositions that have the same truth values in all of their cases. A compound proposition, for example, P and Q, are logically equivalent if and only if Q is a tautology. If P, if and only if Q is a tautology. And the way we would note the logical equivalence is by using a special operator, the equivalence operator. Now, note that this symbol is not a logical connective, and P is logically equivalent to Q is not a compound proposition, but basically all it states that P if and only if Q is a tautology. Sometimes the symbol is also written as like that. And so I guess the next step would be to show you guys a truth table to prove an equivalence. So let's say we have P or Q, the statement P or Q is logically equivalent to the statement not P, and not Q. So let's quickly go ahead and draw out our truth table. So we'll have P, Q, not P, not Q, not P and not Q, not P and not Q, and P or Q. The order doesn't matter in the truth table as long as you're comparing the correct columns, P or Q, and not P and not Q. So since there are only two variables in this example, we're only going to use true, true, false, false, true, false, true, false. Not P would be false, false, true, true. Not Q would be false, true, false, true. Not P and not Q, false and false is false. This is false, this is false, and this is true. And then the negation of this column would be just the opposite. True, 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 false. And P or Q, true or true is true. True or false is true. False or true is true, false or false is false. And as you can see, if we compare this column to this column, well guess what? All of the truth values are identical. So that is one way that you would prove that P or Q is logically equivalent to not P and not Q. And I think we're going to stop it there this time. In the next tutorial, we'll go over some of the equivalence laws. As always, make sure to subscribe for your daily Discrete Math tutorials.